Hi everyone, this is lecture 2 on the topic design of reinforced concrete structures, especially flexures. So today we are going to see effective span, effective depth, effective cover, moment of resistance of doubly reinforced and T-beams. In the previous lecture we have seen the moment of resistance of singly reinforced beams and then how to arrive the stress strain relationship for concrete. So in this video also we will see the how to arrive the stress strain relationship for mild steel and tar steel. So the topic is analysis and design of flexural members. So assumptions, I have detailed these assumptions of limit state of collapse in the previous lecture, that is lecture 1. Clause 38. So the assumptions are plane sections normal to the axis remain plane after bending. Maximum strain at the outermost compression fiber is taken as 0.0035. Relationship between the compressive stress distribution in concrete and the strain in concrete may be assumed to be rectangular, trapezoidal, parabolic, or any other shape, which results in prediction of strength in substantial agreement with the results of test. Um, an acceptable stress strain curve is given in figure 21. So these are all things we have seen in the uh, previous lecture. So what we have not seen in the previous lecture that we will see now. So if xu by d, this is the xu by d is greater than the limiting value, that is limiting value is xu max. If xu by d max by d, if it is greater than this, then the section should be redesigned. So over reinforced xu by d should be less than the xu max by d. At any cost, the over reinforced cannot be allowed as per the IS 456 2000. In the above equations, xu is depth of neutral axis, d is effective depth, fy is characteristic strength of reinforcement, ast is the area of tension reinforcement. So then if it is tension reinforcement, there will be something called compression reinforcement also. Ck characteristic compressive strength of the concrete, b is the width of the compression phase, mu limit is the limiting moment of resistance of a section without compression reinforcement. So this is the mu limit without compression reinforcement. So note down this point, without compression reinforcement. Xu max is the limiting value of xu. So G 1.2 section with compression reinforcement. So that is called, once there is a term called compression reinforcement, tension reinforcement, and there is another term called compression reinforcement. What does it mean, compression reinforcement? To the compression reinforcement always located in the compression zone of the beams. There are two zones, right? One is tension zone and another one is compression zone. That reinforcement provided below the neutral axis, that is tension zone, is called as tension reinforcement. The reinforcement provided above the neutral axis, that is in the compression zone, that is called as compression reinforcement, where the ultimate moment of resistance mu minus mu limit equal to FSC ASC into D minus D dash. So the D minus D dash is the FSC ASC. ASC is the area. This is the yield stress. So stress in the area is nothing but force. So this is nothing but the force, and this is the lever arm. So mu minus mu limit, that is equal to FSC AC into D minus D dash. So how do we arrive this equation? That I will explain in the coming slides, where mu limit are same, and D are same as G 1.1. FSC is a design stress in compression reinforcement corresponding to a strain of 0.0035 XU max minus D dash divided by XU max. So all these things derivation we'll see in the coming slides, where XU max is the limiting value of XU from 3.38.1. AC is the area of compression reinforcement, D dash is the depth of the compression reinforcement from the compression phase. The total area of tension reinforcement shall be obtained by equation AST equal to AST plus 1 plus AST2, where AST is the area of total tensile reinforcement, AST1 is the area of the tensile reinforcement for a singly reinforced section. For MU limit AST1, and remaining part, that is AST2. So AST2 is arrived with this formula ASC FSC divided by 0.87 FY. So analysis class 22, that is analysis, say 22.1 general. All structure may be analyzed by the linear elastic theory to calculate the internal actions produced by design loads in lieu of rigorous elastic analysis. So elastic analysis is rigorous and you need more complicated equations. Linear elastic theory is simple equations and simplified form is presented here. A simplified analysis given in section 22.4 for frames, uh, as given in 22.5 for continuous beams may be adopted. For frames and for continuous beams, the simplified linear elastic theory based analysis were given. Then they have spoke about in 22.2. Here they spoke about effective span. Unless otherwise specified, the effective span of a member shall be as follows. So what are all the condition? This is the condition of a simply supported beam or slab. The effective span means the distance between um, uh, two beams, two supports actually. So that's called effective span. How do we arrive this effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of the slab. So what is in the clear span, that I will show in the coming slides. Or center to center supports whichever is less. So that I will what is the how the figure looks like, that I will show in the next slide. Um, Continuous beam or slab. In the case of continuous beam or slab, if the width of the support is less than L by 2, sorry, 1 by 12 of the clear span. So clear span here you can mention it as L0. So L0 by 12, width of the support is less than the effective span shall be 22.2.A. So this is the 22.2.A. If the supports are wider than 1 by 2, 1 by 12 of the clear span, that means L0 by 12 or 600 mm, whichever is less, the effective span shall be taken as under. So first point, the end span, this is the end span. This is the width of the supports. So width of the support, and this is the width of the support. Clear span means distance between two supports, not center to center. This is the face of the support, one support, from one face of the support to another face of the support. The distance between these 2 points is clear span. For end span with one end fixed. So you can see the end support, it is fixed. So you can see this is fixed. End support is fixed and other is continuous. So one end is fixed and another ends are continuous. Continuous for intermediate spans. So these are the intermediate spans. The effective span shall be clear span between the supports. So this is the effective span. This is a clear span between the supports. Then second case, uh, for end span with one end free and other end continuous. One end is free end and other ends are continuous. So this is continuous. Other ends are continuous. Effective span shall be equal to the clear span plus half of the effective depth of the beam or slab, or clear span plus half of the width of the discontinuous support. See, this is the width of the discontinuous support. This is the width of the discontinuous support. So either clear span plus half of the effective depth of the beam. So effective depth of the beam or slab, this is the effective depth. So clear span, this is the clear span. So clear span plus half of the effective depth of the beam or slab, or the clear span plus half the width of the discontinuous support. So either this is the half of the width of the discontinuous support, whichever is less. In case of spans with roller or rocket bearings, the effective span shall always be distance between the center of bearings. So that I will show in the next slide. The cantilever, if in case of cantilever, the effective length of the cantilever shall be taken as its length to the face of the support. So if it is a cantilever, if there is a cantilever and this is the face, so this is the face of the support plus half of the effective depth shall be taken as its length, effective length to the face of the support plus half of the effective depth, except where it forms the end of a continuous beam, where the length of the center of support shall be taken. Length to the center of support. In frames, in the analysis of continuous frame, center to center distance shall be used. So in some cases, if the scenario is very complex, the best thing is center to center distance. So here you can see the point 3 with the roller or rocket bearings. So this is the roller. So the center to center distance is the effective span. So L effective is equal to L clear span plus D by 2 or L clear span plus width of discontinuous support, whichever is less. This is for the condition of uh, this case. In general, this can be the summarized thing. L clear plus D or center to center distance of span, whichever is less, when L clear span by 2 is less than the this one. Then clear span between the supports, L clear span plus D by 2, L clear span plus W discontinuous support divided by 2. So whichever is less, then the center of bearings. So this is the third case. This is the third case, and this is the first case, and this is the second case, and another one is the third case. Then effective depth. What is in the effective depth? Effective depth of a beam is the distance between the centroid of the area of tension reinforcement. So this is the tension reinforcement. Here you can see two numbers of say D diameter bars. So here you can see four numbers of say D diameter bars. So here you can see six numbers of D diameter bars. So the centroid of the area of the tension reinforcement. So this is the total area. In this total area, the centroid passes through the midspan or midpoint. This is the centroid line. Centroid passes through the midline. So here, this is centroid. And here, this is centroid. And the maximum compression fiber. So this is the distance between the maximum compression fiber is this one, and the distance between the centroid of the area of the tension reinforcement and the maximum compression fiber. So here you can see a simply supported beam. So these are supports, and this is the beam, and this is clear span. This is center to center of supports. So which one can be taken as effective length? So that is given here: clear span plus effective depth or center to center of supports. Whichever minimum of these two shall be taken as L effective, that is effective length. So always we have to take, when there is a moment, effective length is very crucial for deciding the bending moment, for design and everything. So maximum compression fiber excluding the thickness of the finishing. So after the beam, there will be some finishing. So this can be a cover, and this can be a cover or finishing. Cover or finishing with the member and thickness of any concrete provided to allow for wear. So this will not apply to deep beams. So also note down this. Those who are doing research in deep beams should have understanding on this concept of effective length, effective cover. Uh, of course, effective length is part of the analysis, but effective cover cannot be applied, or effective depth concept cannot be applied for deep beams. For T-beams and L-beams, a slab which is assumed to act as a compression flange of a T-beam or L-beam shall satisfy the following. The slab shall cast integrally with the web. So always T-beams, the design is name is T-beam, but actually it was or it shall be cast integrally with the web, or the web and the slab shall be efficiently bonded together in any other manner. So, in concrete beams, there is always it is cast together. So, therefore, the bonding is assured. If the main reinforcement of the slab is parallel to the beam, so this is the beam actually. So, here you can see the figure 3, that is transverse reinforcement in flange of deep beam or T beam when main reinforcement of slab is parallel to the beam. So here you can see the beams. So here there is this is a beam. So here you can see the beams. So here they are saying if the main reinforcement of the slab is parallel to the beam. So if this is the main reinforcement and this is the beam, so you can see the beam, I can see the beam and the main reinforcement. This is the main reinforcement. Main reinforcement runs parallel to the beam. Transverse reinforcement shall be provided as in figure 3. So we have to provide the transverse reinforcement. Such reinforcement shall not be less than the 60% of the main reinforcement at the mid-span of the slab. So we have to provide the transverse reinforcement. Effective width of flange. For T-beams, effective width or flange is, that is BF, is very essential to be found. So that is L beams. This is isolated beams, and this is L beam, and this is T beam. In the absence of more accurate determination, the effective width of the flange may be taken as the following, but in no case greater than the breadth of the web. So this is the breadth of the web plus half the sum of clear distances to the adjacent beams. So here also you will get one more beam. So here also you will get one more beam. So this is clear distance and this is also a clear distance. So these two clear distance needs to be added, sum of clear distances. So this is the clear span. This needs to be added and this needs to be divided by 2. That is the upper limit criteria for BF. In case of isolated beams, the BF cannot be, no case can be greater than its actual width. So this is the actual width actually. For T beams, the breadth of the flange is equal to L0 by 6 plus BW plus 6 into DF. For L beams, L0 by 12 plus BW into 3 into DF. So in this way, for isolated beams also L0 by B plus 4. So BF, that means flange width, effective flange width, is a function of depth of the flange, width of the web. So three terms. Df means depth of the flange, and L0. L0 is the distance between points of zero moments in the beam. Df is the breadth of the beam, df is the thickness of the flange, b is the actual width of the flange actually. So this is the things. And one more thing, for continuous beams and frames, L0 shall be assumed as 0.7 times the effective span. The stress strain curves for reinforcement. So here the representative stress strain curves for reinforcement. This is cold work deformed force. That means FE 415, FE 500, FE 500, FE 550, FE 550D, FE 500D, FE 550D. So these are all the cold work deformed bars. In these cases, you will not have any definite yield point. So there is a linear portion. So this is the linear portion. So that is representing the elastic behavior, where Young's modulus equal to 2 into 10 to the power of 5 Newton per mm square, and the remaining portion you can see a constant plateau-like region. So here you can see the 0.8 Fy, 0.9 Fy, 0.97 Fy are the terms you can able to see. That means 97 percentage of the Fy or 95 percentage of the Fy. So that is approximately equal to 0.000003 or 0.001, 0.002, and 0.003. And in case of mild steel, you will have a definite and yield point. So initially it is linear, and then you can see a plateau-like region, and this is constant. In this portion, the initial portion Fy by 1.15 is the design yield stress for mild steel, for TOR bars, that means torque bars or cold work deformed bars. So here our yielding strain shall be Fy divided by 1.15 plus 0.002 is the yielding strain. So balanced or limiting neutral axis. So here this is the beam actually. The strain distribution. Then how the strain is distributed throughout the length, throughout the depth is shown here. So this is the depth at level 1. Say you can level 1, and this is level 1, and this is level 2, and this is equal to, you can see, level 3. So at various points the strain is measured using demountable mechanical strain gauge. So these 2 points, you know the deformation. So strain at level 1, and this is strain at level 1, and this is strain at say, sorry, this is level 0, strain at level 1, and this is strain at level 2, and this is strain at level 3. So if you plot these 3 points, you will get this straight line. So this is how the strain plot is plotted here, and this is the neutral axis, where there is neither compression strain nor tension strain. That's why the strain at the neutral axis is 0. So it is further detailed here. The limiting neutral axis. How do we arrive the limiting neutral axis that I have explained in detail in the previous lecture? The limiting strain is 0.0035 in concrete. So how do we arrive this limiting strain? So this is the stress strain curve of concrete. Initially it is parabolic, and after that it is linear or initially it is parabolic, and then if it is constant. So in constant portion, the maximum strain is 0.0035. So that's how the strain 0.30035 has arrived. So usually then the depth of neutral axis is measured from the top actually. So this is the top or compression fiber, top fiber. This is top fiber, and XU is measured from the top. So if the XU is less than the measure XU limit, so this is the XU limit. XU limit. Limit is, that means limiting neutral axis depth, or based on the limiting strains. So at exactly when the neutral axis reaches the limiting strain, then the strain at the concrete should be 0.0035. So in case of under reinforced, the strain in concrete should be less than the 0.0035, and in case of over reinforced, strain in concrete should be greater than 0.0035. XU, if the XU limit, so this is the XU limit. When the XU is less than XU limit, then it is called under reinforcement. So XU is greater than XU limit or balanced section, that's called over reinforcement. So exactly at this point, you can say this point, there you can say under reinforced section, and if the neutral axis or the strain distribution crosses here, then it is called over reinforced section. So the strain also, you can see three types of strain you can see here. So one part is the strain. This is a yielding strain. Yielding, what is the yielding strain of reinforcement? Fy divided by 1.15 ES plus 0.002. This is the yielding strain. So in case of over reinforced, so the the strain in steel would not reach, may or may not reach the yield strain, but the concrete reaches the yield strain, reaches and crosses the yield strain. In case of under reinforced, the strain in concrete reaches first. So, sorry, strain in steel reaches first. So this is strain in steel, that is tension reinforcement always greater than the yield strain for under reinforced section, and it may be or may not be less than the um, um, yield strain for over reinforced sections. But in case of concrete, the point is very clear. If the strain in concrete exceeds 0.0035, then it is called over reinforcement. If the strain in concrete less than 0.0035, then it is called under reinforced sections. So that's what the code limits using these three values for FE 250, FE 415, and FE 500. So how do we arrive these values of 0.53, 0.48, and 0.46? As per codal provisions, XU max by D values uh, can be arrived using this following derivation. So you know the strain distribution. So this is the strain distribution. So this is a strain distribution. So here you can see this is XU and this is the total depth D. So D minus XU. So this is the term called 0.0035 and this is strain in steel. So this is how this um, uh, epsilon st is arrived. So d minus xu equal to epsilon st into xu. That d minus xu in the 0.0035 minus xu epsilon st equal to 0. Then it is further rearranged as xu by d equal to 0.0035 divided by 0.0035 plus epsilon st. This value is given in IS 456. Then strain diagram relationship, that is using this formula, we just simply substitute the strain in steel. What is the strain in steel? Epsilon st for mild steel is equal to Fy divided by 1.15 Es. So in this case, just if you substitute this value here and you know what is Es and what is Fy. So Es is known, Fy is known. Just substitute these values. So you get Xu max by D value as 0.7368. But code is giving as 0.53. Why 0.53? We will see in the next slide. Why IS456 give 0.53 and not 0.76? So here the unified strain values were taken. Epsilon st equal to 0.002 plus Fy divided by 1.15 Es. So this is the strain value. So this strain value is substituted here. So using the existing equation, you know the what is the strain value. So this is Fe 250, Fy equal to 250, Es equal to 2 into 10 to the power of 5. So 0.87 Fy divided by Es equal to 0.001 and Xu by D value is equal to, so this is nothing but Xu by D, that is equal to epsilon st epsilon st. So just substitute this value with this value and you will get 0.531. So for Fe250 also we are pressing that um, uh, there should be a ductile failure, and for another reason that strain that in steel should yield first. So steel yielding before concrete crushing. This is ensured. That's why this formula strain in steel epsilon st is used here. Strain in steel 0.001 Fe415 was used here. Then while computing, it is what is the Fy by 1.15 Es and design of trial, then Xu by D is equal to 0.49, that is equal to 0.48. So in other case, the same formula is used. Fe415, in case of Fe415, you get Xu max by D value is equal to 0.46. So same formula is used here. Xu by D equal to 0.0035 divided by 0.0035 plus epsilon st. So using this formula, you will get 0.46 for Fe415. Now for Fe500, sorry, this is also, this is 500. So Fe415, the Xu max by D value is equal to 0.48, and for Fe500 the Xu max by D value is equal to 0.46. So this is the code specified xu max by d values. So limiting steel area and limiting moment. So how do we limit the, how do we arrive the AST limit? We have to just compare the, equate the compression force and tensile force. So when the XU equal to XU max, AST is equal to AST limit. So the limiting AST equal to 0.36 FCK B into XU max divided by 0.87 Fy. In normalized form, limiting reinforcement ratio P limit. So P limit is the limiting tension reinforcement. So P limit equal to 0.83 FCK XU max by D 0.87 Fy. So a limiting moment for rectangular section is often shown in compact numeric form in the textbooks as um, 0.36 FCK B into XU D minus 0.42 XU with XU equal to XU max. So now we are going to see moment of resistance of doubly reinforced sections. Why do we need doubly reinforced sections? Doubly reinforced beam is a beam reinforced with steel bars in both the tension zone and compression zone. So why do we need doubly reinforced beam when depth is restricted? Where the reversal of stresses? What is in the reversal of stresses? In earthquake forces, the force will act on both sides actually. So if this is the frame and the stress will act in this direction and also in this direction and also in this direction. So this is called stress reversal on both directions, cyclic loading. These are all the best example for the cases of stress reversal. In those cases, the tension reinforcement tension and compression reinforcement will act will act better than the will perform better than the singly reinforced beams. To control deflection and cracking, compression reinforcement helps. A doubly reinforced beam offers several advantages over a singly reinforced beam. Nowadays, we are providing at least minimum number of bars in the compression zone to avoid any stress reversal. It provides high moment carrying capacity without increasing the depth of the section, which is practically useful for beam depth is restricted. So, main advantage is the aesthetic point of view or architectural point of view. When the depth is restricted, it a design engineer can choose doubly reinforced beam. The presence of compression reinforcement improves ductility and stiffness of the beam, helping the control of deflection and cracking under service loads. It also enhances the beam's resistance to stress reversal. So I told what is in the stress reversal. So it has the resistance for stress reversal. However, there are small disadvantages as well. Design and detailing of the double reinforced are more complex. Congestion. Main problem is that congestion. So that means concreting is quite difficult. Additionally, the use of extra steel increases the cost and weight of the structure. Despite these drawbacks, double reinforced beams are often preferred when strength, stiffness, durability are more critical than economy. Of course, nowadays all the beams we look after the strength, stiffness, and durability over the economy. So strain profile and stress block details for doubly reinforced beam. So this is the compression reinforcement. So this is the compression reinforcement and this is the tension reinforcement. This is the tension reinforcement. And here you can see this is a neutral axis and D dash is the effective means cover, not exactly effective depth. So this is the distance between the compression reinforcement, centroid of the compression reinforcement and the extreme compression fiber. D is the effective depth, and K1 XU, K2 XU is the distance where the stress blocks two portions, depth of the stress block portions, rectangle and parabolic, and the first portion is parabolic portion, and first portion is the rectangular portion, second portion is parabolic portion, and here the strain profile is shown here. So I have explained in detail about the strain profile. So then the stress block details. Here the stress block means x-axis is the stress and y-axis is the strain. Sorry. Yes. Y-axis is strain, and also it is also representing the exactly the depth of the beam. So here the strain is for 0.002 and 0.0035, and the stress is 0.447 FCK. So how the depth, how the new strain is plotted, that I explained in the previous slide. So maximum strain in steel is point Fy divided by 1.15 ES plus 0.002, and strain in concrete is 0.0035. So the forces acting on the rectangular portion is nothing but the 0.447 FCK into 0.43 XU. So how did we arrive K1, K2? That I have detailed in the lecture 1. So 0.4, say, um, so K1 is arrived as 0.43 XU, and uh, K2 is arrived as 0.57 XU. So this is K1 XU and this is K2 XU, and so here the 0.447 FCK, 0.43 XU into B. So this is the stress into that area is so this is 0.447 FCK, this is base, and this is height actually. What is the height? The height is exactly 0.43 XU. So this is base in the height, then 2 by 3 base in the height is in the B, so it's nothing but the C2 force, and the C is the compressive force, 0.36 FCKB in the XU. Here Z equal to depth of lever arm, and then where D equal to 0.42 XU. How do we arrive the depth of lever arm? That I explained in the lecture 1. Tension force is T equal to 0.87 FYST. Compression force is 0.36 FCKB in the XU. This is for singly reinforced beam, and how we are arriving the doubly reinforced beam is shown here. Here C1 is the compression force in the rectangular portion. This is parabolic portion. Rectangular portion, and this is parabolic portion. So, and C is C1 plus C2. So that is you are getting 0.36 FCK XU into FCK. And the next portion is the force due to the compression steel. So this is force due to the compression steel. So this is the rectangular and parabolic portion. This is the compression force of singly reinforced. This is the force acting in the compression zone for a singly reinforced beam. So that is CC, and CS is the compression steel reinforcement. So for that, how much amount of area is reduced, and here if this is your beam and this is the tension, and this is the compression reinforcement, this is the tension reinforcement, and this is the compression reinforcement, and this compression reinforcement is ASC. So here ASC in the force. So this much amount of concrete is less actually. So because this AAC concrete is replaced by reinforcement. So that's why ASC. So what is the force acting in this portion? That is 0.447 FCK in the AAC is the force acting in these two hollow points or where the reinforcement exists, and that should be subtracted from the FSCAC. So FSCAC is the compression force. FSC is the strain, stress in compression reinforcement. So S is stress and C is compression reinforcement. That is F, that is stress, not exactly yield stress, you can say stress in steel reinforcement provided in the compression zone, that is called FSC. FSC ASC minus 0.447 FCK ASC. So that needs to be subtracted, and C that is equal to CC plus this portion, that is CS. You will get the total term C. So T equal to 0.87 Fy AST. So just we equate these two forces CC plus CS, that is equal to T, and you will get neutral axis depth XU equal to 0.87 Fy AST plus 0.447 FCK-ASC minus FSC-ASC divided by 0.36 FCK into B. So what is MU? MU is nothing but the compression force in the lever. So the lever is nothing but D minus 0.42 XU. So and the compression force in D minus D dash. So this is the lever arm. This is the lever arm, and here this is the lever arm distances. So that based on this, MA limit is nothing but 0.36 FCK B in the XU max into D minus 0.42 XU max plus FSC AC minus 0.447 FCK AC D minus D dash. So this is the MU limit or limiting moment of resistance for a doubly reinforced section. Now, moment of resistance of a T sections. So here three cases. This is case 1 and this is case 2 and this is case 3. In first case, the neutral axis, then this is the neutral axis fall in between the depth of flange. So this is the depth of flange, so DF. So here you can see the DF and this is DF. Within the depth of the flange, and this whole parabolic portion and rectangular portion falls within the neutral axis, within the flange. So you will get like this is just like a BF, beam of width BF. So the moment of resistance, everything is very simple as like a singly reinforced beam. So where the compression force is 0.36 FCQ, tensile force is 0.87 FY, AST lever arms is equal to D minus 0.42 XU. In another case, neutral axis, in other two cases, neutral axis falls in the web portion or below the flange portion. So this is the flange portion, and this is up to this is a flange portion. So in these two cases, whether the depth of the flange is less than 0.43 XU or not, that means rectangular portion, whether it falls within the flange portion or it falls uh, up, falls beyond the whether the rectangular portion falls beyond the flange portion or not. So these are the three cases. So in both the cases, y equal to d minus yf by 2. So this is, they have given simply given d minus yf by 2 is the lever arm they have given. So one case yf is nothing but df. In another case yf is written in a little complicated equation. So that we will see in the next case. So this is the case one, where case one is a simple formula: 0.87 FYAST D minus 0.42 XU. In case of uh, uh, compression zone, point F3 FCK B in the F, this is F, BF in the XU, D minus 0.42 XU. Same formula is used here. So this is the simple formula is used, BF. In case of moment of resistance for case number 2, and this is for case number 3. So for case number 2, the point is that neutral axis uh, falls below the depth of the flange. So this is the depth of the flange, and this is the depth of the flange. So neutral axis falls below the depth below the depth of the flange. So this is depth. In this case, the df, here you can see categorically that df is greater than the 0.43 XU. That means the whole portion is nothing but the same as usual. The compression force is nothing but 0.87 FYAST, f 0.8 447 FCK into 0.43 XU into BWO. Then remaining portion is 2 by 3.447 FCK into 0.7 XU into BWO. So this is nothing but 0.36 FCK XU into BWO. Here the compressive force, see this is for web portion. So next you have to find for web portion and flange portion. So there are two portions. So this is web portion and this is flange. This is flange portions. So compressive force needs to be found in two levels. One is for web, another one is for flange. So here for flange only the terms little bit changes. That is 0.445 FCK B minus F into BWO. So here B minus F into BWO divided by 2, and this portion is also BF minus BWO divided by 2. So that is B minus into DF. So this is so simply instead of YF, here you will get DF. This is YF. So moment of resistance equal to, this is web portion, this is web portion, and this is flange portion. So this is the force, and this is a lever arm. This portion is the lever arm. Here the D minus 0.42 XU is the lever arm. So exactly say this is the lever arm. So mu equal to 0.36 XU max by T minus 1 minus 0.42 XU max by D FCK BWO D square. That means web in the D square 0.45 FCK BF minus BWO DF in the D minus DF by 2. So in case 3, for this is the case 3 where the I can draw in detail actually. So in this case, if this is the beam, and this is your flange width, and here your um, and this is your flange width, and here you can see um, so this is the flange depth, and this is the neutral axis, and this is the 0.43 FCK, the 0.43 XU. So of course your depth of the flange, that is DF, DF is greater than 0.43 XU. So this is the neutral axis and this is 0.43 XU. So your DF is greater than 0.43 XU. In that case, YF is equal to zero point 0.15 XU uh, plus 0.65 df. So yf is a function of xu and yf is a function of xu, that is depth of neutral axis and depth of flange. So here the compressive force is of the web is nothing but 0.36 FCK. This is web portion 0.36 FCK B into XU. Then flange portion is nothing but the old formula only 0.445 FCK BF minus BW into YF. So this portion is BF minus BW divided by 2, and this portion is also BF minus BW divided by 2. So this is a flange portion into YF. So here the YF is nothing but a point. So this is nothing but YF. Moment of resistance same like a force, compression force in the lever arm, and this is also the compression force in the lever arm. D minus YF by 2 is the lever arm. So this is the lever arm. So moment of resistance equal to mu equal to 0.36 XU max by D 1 minus 0.42 XU max by D FCK BW D in D square. So this is for web portion, and 0.45 FCK BF minus BW into YF into D minus YF by 2. This is for flange portion. So total moment of resistance is moment of resistance offered by web and moment of resistance offered by flange. The limiting moment is just a replication of these things. Same equation. So IS code provided the same equations in the uh, G 2.1, T 2.2, 2.2.1 and 2.3. So the same equations are provided here as limiting. So IS code specifies in two cases only, case 1 and this is case 2. In case 1, the flange, so df by d does not exceed 0.2, and in that case the limiting value of moment of resistance of the section may be obtained by the following equation when df by d does not exceed 0.2. So in those cases, so we use this formula mu equal to 0.36 xu max by d 1 minus 0.42 xu max by d fck bw into d square. So this is for web, moment of resistance of the web, and this is the moment of resistance of the flange. 0.45 FCK BF minus BW DF into D minus DF by 2. So in case of DF, so this is DF by D exceeds 0.2. So in those cases, the moment of resistance is given by this equation. So web portion is same, the flange portion is 0.45 FCK BF minus BW into YT D minus actually is YF only. YF by 2. So for XU max, if this is not DP, this is DF. When XU max is greater than XU and it is greater than DF, the moment of resistance may be calculated by equations in G2.2 when DF by XU does not exceed 0.43, and G22.2.2.1 when DF by XU exceeds 0.43, in both cases substituting XU by XU max. So these are the codal provisions. I just briefed the codal provisions here. Thank you.